All right. Welcome everyone to Hacker Earth webinars. My name is Amit Sethi. I will be presenting this webinar on evolution of CNNs for image recognition. A brief introduction. I am an assistant professor at IIT Guwahati, Indian Institute of Technology. And previously I've worked in a management consulting firm. My research is in computational pathology and I use deep learning for that. And I've got my PhD from University of Illinois at Urbana-Champaign. So the goals of this webinar are basically I want to demystify CNNs, convolutional neural networks. So I want the attendees to become familiar with the components of CNN. I want you to understand the problems on which CNNs are applicable. They are not a silver bullet that should be applied to any machine learning problem. And understand the reasons behind the success of CNNs. So CNN being convolutional neural network. And develop familiarity with ongoing advances in CNNs. So first, I want to introduce shallow versus deep learning. Why deep learning is becoming the de facto way of doing machine learning. So let's say we have a problem in which we want to classify digits. We have images of digits, handwritten digits, and we want to classify them. So in shallow learning, what you will do is here's a system that I'm showing, a typical system for shallow learning. A shallow learning system may also have layers, but the gray layers that you see, the gray ones are not tunable. They don't have any tuning knobs. So you would take an image and you would extract some features, and then you would extract features of features and so forth, and until you go to the final layer where you have a classifier. And this classifier will have numbers that can be changed, and they will be changed based on an optimization algorithm. So those are the knobs that you see here, the black knobs. So when you change these knobs, what you get is you get a better classifier. So the classifier takes an output, takes an error signal from the errors it makes on the training samples for which we know what the class is. So the class being whether this image is 7 or 5 or 3 or whatever that is. Compare that to deep learning. In deep learning also you have multiple layers, but like you see here, you have multiple of these red layers. Red layers means these layers have tunable knobs. They have tunable parameters that can be changed using a training algorithm, which is an optimization algorithm. So it is deep in the sense that there are multiple layers of multiple trainable layers stacked on top of each other. So let me give you a concrete example. So let's say you have images, and these images are represented by a matrix of pixels. And if you see a white dot, that means the pixel value is high, let's say 255. And if you see a black dot, then the value is low, let's say 0. So if you give this, the matrix of pixels for a digit, and let's say it's a fixed size matrix to a support vector machine, what it will do is it will, so let's say if this is 28 by 28, 28 width and 28 height, then all these 786 parameters, all 786 pixel values will be fed into the support vector machine, and it will change its support vectors and the weights of the support vectors of the kernel function and so forth, until it gets the best classification for the training samples for which you know the classes. Now, the problem with this is that without any intervening layers, if you look at two images of 5, for example, and if you look at the overlap of black pixels between this image and this image, what you will see is that there is not a whole lot of overlap. So although these two are both 5, there is not a whole lot of overlap, and that is a problem, right? So if you change this, if you have the same object which is 5, but you change its shape. You move it slightly, which is translation. You move it, or you scale it up or down. You make it bigger or smaller. That is scaling. Or rotate it slightly. When you write handwritten digits, you don't write it the same way every time, or warp it. Then would you be able to recognize the same digit? And let's say if these images are more complex than just handwritten digits, if these are any of the thousands of object classes that we encounter in our everyday vision, then it becomes an even bigger problem. So even before deep learning, layers of processing have been added to shallow learning also. So for example, you wouldn't just classify pixels. What you would do is you would take an image, you would detect something called interest points, and these interest points are things like corners, and corners of any image, in any image, define the shape of the object that is inside that image. And then you would describe, you would extract some descriptors from that. So these descriptors are basically how are the edges oriented around that interest point. So if you see a horizontal edge or a vertical edge or a slanted edge and so forth, and then you would form some sort of a histogram so that it becomes each image can have different number of interest points, so you standardize it so that the histogram has the same number of bins, and then you put it in a classifier like support vector machine, and it will tell you what object class it is, in this case what digit it is. So you can already see that we are even before deep learning, we were not feeding pixels directly into the classifier. We were extracting features and then features of features, and then we were going to the classifier. But the difference was that this hierarchy of feature extraction earlier was fixed. There was nothing to be changed in it. Only the classifier parameters were to be changed. Now, would this set of features still work if we were looking at a different set of images than digits? How do we know whether the features that we have extracted, which in our case is interest point descriptors or histogram of interest point descriptors, how do we know that they are optimal for the given data set? And what if the input data set changes? Instead of digits, it's everyday objects. Would it still be valid? So in other words, is there a principled way that we can learn a feature hierarchy instead of having a fixed feature hierarchy? So that's where deep learning comes in. So the way deep learning started was, it was originally conceived of much earlier in the 60s in form of neural networks, but these neural networks were not trainable to the extent the way they are trainable now. So I'll explain that in a minute. So what a neural network is, it's basically a network of simple functions. So each of these circles that you see here is a function. So each of these circles here is a function. And one function, the output of one function goes to several functions in the next layer, or the several neurons in the next layer, and then from next layer to the next layer and so forth. So in this case, you have one set of neurons that just represent the input. In this case, in the previous example, this would be the pixels of the image. Then you have a hidden layer, hidden in the sense that it is not visible to the outside world. And then you have an output layer where you get the labels, whether it is digit 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. So there would be 10 output nodes. So the number of hidden nodes you would change based on the complexity of the problem. Okay. So each of these functions, whether it is in the hidden node or in the output node, they do something very simple. They multiply all of their inputs with some weight. So for example, if you look at this input xi in the input layer, and then this xi is multiplied by a weight wij, w from I to j, the weight from I to j. And that is, if you look at the equation on the right, that is this multiplication, wij times xi. So you would do that for all the inputs, and you would add some constant, and you would pass it through some function f, and that would be the value that this node hj computes. So one simplification that was already made in neural network structure was that if you look at this input layer xi, it does not provide input to one layer beyond the next layer. So it is only connected to the next layer. So that controls a number of connections in this. Yet this number of connections can become very huge, and we will come to that in a minute. So let's say, what do we have to do to make this neural network work in the sense that it classifies your input correctly, in whether it is an object class or whether it is a digit or whatever. So let's say you are looking at an output yk and your output is wrong. That means it is not classifying the correct digit. So you want to have this error that you compute here. This error has to be sent back to the other nodes, and these weights wjk and wij have to be changed. So it's a credit assignment problem. So this error signal will go back, and there is a mathematical formulation of it, which is called gradient descent, and the efficient form of it is called back-propagation. So this error is back-propagated. So why it is called back-propagated is because when you give the input down below here, then it is forward propagated to the hidden nodes and then forward propagated to the output nodes. But when the output node doesn't perform well, that error is fed back from the output node to the hidden nodes, and then from hidden nodes to the input nodes. But when it passes through these weights, these connections, these lines, it changes the weights. And how you change that weight is basically the training algorithm that makes neural network learn over with more and more examples. So the more inputs with known outputs that you give it, and it computes an output and compares it to the known output or the target output and finds out that there's an error, it will try to improve itself. The back-propagation algorithm will try to improve the performance of the neural network. Now the problem with this is that this error signal that passes back, now if you look at one particular weight here that connects, let's say, xi to hj, how do we know how much credit, how much weight, or how much contribution it has in the error? So the error is coming from all these other paths, all the connection of these lines and these lines. So there's a lot of the error is distributed among so many different weights that we don't know how to do this. I mean, we know, but it becomes very small signal to effectively train or effectively change these weights. And now imagine you add multiple hidden layers. Okay, so not just one hidden layer, but 1, 2, 3 maybe. Okay, so now look at how complex this weight interconnection is. So in general, if you have a machine, a learning machine, which has a lot of tunable parameters, which are the weights in this case, then it becomes more and more difficult to tune it. Okay, it becomes, these are so many different knobs that you have to slightly tune so that the machine performs well. So what is clear is that we do want a deeper hierarchy. Why? Because we think that extracting features in one hidden layer and then features of features in another layer and features of features of features in another layer and so forth, the deeper we go, the better representation of the input we get and the easier our classification is in the end at the output layer. So we want a deeper hierarchy, but we don't want so many bits. Okay, so a way to think about how depth helps is, let's say your first layer will extract all the edges, slanted edges, horizontal edges, vertical edges, and then next will extract combination of edges and so forth, and then some recognizable parts in the end, and then the complete object in the last layer. So how do we control the architecture? How do we control the number of weights and yet have depth? So for that, let's look at this some of these weights carefully. Okay, so one of the ideas is that let's not have the weights be completely independent. Let's share some weights. Let me give you an example of what that weight sharing means. So if you look at this particular neuron and it is connected to the previous layer, this neuron, the hidden layer 2, is connected to 3 neurons in hidden layer 1. And let's say I represent these weights by these colors, red, blue, and green. Now if you go one neuron to the right, and let's say I constrain that its weights are exactly the same in the same order. Then the three weights are different, but they are exactly the same to the corresponding weight in the neuron on the left. Okay, so in that case, if algorithmically or architecturally I constrain that these weights have to be the same, then I don't have two red weights. It's actually just one number. It's one number that represents two red weights, and I can repeat that over the next neuron and the next neuron and the next neuron and the next over all the neurons in this. So basically these neurons share weights. Their weight structure is exactly the same. The values of the weights are exactly the same. In fact, they are not separate neurons, but they are the same neuron applied in different locations. And the number of inputs that it gets is not the entire previous layer, but a small portion of the previous layer. So this concept is called convolution. So in convolution, here I'm showing this black signal or a black, let's say, these are the outputs of, let's say, the previous layer, and the x-axis is the location on the layer. And if you look at the green box is the weights of one particular neuron. Now if I go to the next neuron, the same box or the same shape goes to the next neuron and so forth. So it's basically sliding over the input, and when you take the sum product of that, what you get is this red signal. That's the output. So that it takes element-wise product, adds the products, and the resulting value is put in the location in the feature map. So you can do this in more than one dimension also. You can, and that's what image recognition convolutional neural networks do. They do this convolution in two dimensions. So if you look at this small square is represent the weights of a neuron, and this is basically a convolutional kernel. And this big square is the input, is the previous the previous feature map. So now when this kernel, this 3 by 3 convolutional kernel takes a sum product with each of these locations, 3 by 3 locations in the previous map, and computes and puts the output in the next layer, that's two-dimensional convolution. Okay, so the way to think about it is that your previous layer was 6 by 6. You have 6 elements here and 6 elements here. So let's say it's going to be much less than 6 to the power 4. So each neuron also processes only a patch of the previous layer. It doesn't process the entire image. It processes only a part of it, which is same as that. So what is it actually looking for, right? So these kernels are actually looking for patterns that match their own shape, their own distribution of numbers. So in this case, you see there's a 5 in the middle and there are minus ones around it. So what it is looking for is, if you have a blurred image, it's trying to sharpen it. Okay, it's the middle one is sharper than the other ones. So it's trying to subtract the average from it. So in effect, what it will look for in the image is a high number at the center and low numbers around it. So each kernel looks for exactly what its numbers are, something like that in the previous image. Okay. So this convolution feature extraction works when your signals or your inputs are ergodic. So ergodic, what it means is that you expect to see similar features at different points. So if you take an example of an image, let's say you're looking for you have a classifier, you want a classifier to detect cats. Now the cats have distinctive eyes, but those eyes can be anywhere in the image. So one of your kernels higher up in a convolutional neural network could be an eye detector, and it will slide over the entire image and try to find an eye anywhere it can find. Okay, and then you will not have a single kernel, but you will have a multiple stack of kernels. So let's say you have a because you want to detect not just eyes, but you want to detect whiskers, you sense what. But to learn from data, it requires a lot of data. So we are talking about tens of thousands of images from different types of objects, if not hundreds of thousands, to train convolution. So these features can appear anywhere in the image, so that's why they're called ergodic. And there are only a few meaningful type of patterns. For example, if you go to the lower layers in the hierarchy, let's say there are only few different orientation of edges, vertical, horizontal, and then somewhat slanted and so forth. So to put this in a hierarchy, what Jan LeCun came up with in the late 90s is the first version of convolutional neural network. So in his architecture, when he was looking at handwritten digits and handwritten letters, the convolutional filters were of the size 5 by 5, for example, and they were sliding over the entire image. But there was not just one filter, there were 6 of them. So you would get 6 channels or feature maps as a result of that. And then he was doing subsampling to reduce, I will come to subsampling in a minute, to reduce the size of the feature map. So what subsampling basically does is it says that, let's say I found a slanted edge, it doesn't matter whether it's here or slightly shifted, I'm going to just count it as one slanted edge. It reduces the information to be processed in the next layer. And then he had more convolutions on top of that and so forth, and then some other layers, which I will come to shortly. So if you think about it for a minute, let's say you have a color image of size 32 by 32, and it has 3 channels, red, green, and blue. And in the next layer, you detect 25 feature maps. You have 25 different convolution filters of size 5 by 5 that are going over this. So if it was fully connected between the input and the next hidden layer, you would require 32 times 32 times 3 times 28 times 28 times 25, which is 60 million weights. But if you have just hidden, if you just have convolutional kernels of size 5 by 5 by 3 times 25 of them, 25 different convolution kernels, you require just 1800 such weights. So you have reduced a lot of weights in the process of doing convolution. So what are convolutions good for? Convolutions are good for data that comes on a grid. Okay, so this is very important. If you think of an audio, so audio is samples of sound signal. Text is letters in an order, and protein structure is these amino acids in an order, and then DNA is nucleotides. So all these are one-dimensional signals or one-dimensional inputs that are arranged in an order. But you cannot change the order. You cannot have 2 nucleotides or 2 amino acids change places and it will not remain the same protein. So that order is very important. Okay, whenever the order is important and there are small substructures within that order that you can detect anywhere in the chain, then you can do convolutions to detect them. In images, that convolution, instead of just along one dimension, it becomes 2 dimensions, which is along the width of the image and the height of the image. Similarly, in video, it can become 3 dimensions. Height, width, and time, the frames of the image. What convolution is not good for is when you want to do classification on a data set where you have different variables, but the order is not important. So for example, let's say you want to predict breast cancer risk, and it is dependent on age, whether the person is a smoker, drinker, has children, has breastfed, has BRCA1 mutation, and so forth. Now, it doesn't matter which of, what is the order of these variables. Similarly, whether a loyal customer, what their gender, age, purchase in the past year, and so forth is, the order of the inputs is not important. So whenever you have an input like this, unlike pixels of an image whose order is important, then for unordered data, convolutions are not a very good idea. There are other deep learning models that you can use for that, but convolution neural networks will not be one of those. Okay. So one of the things that we skipped in this LeNet architecture was this subsampling. So this subsampling part is called pooling. And so after usually you will find that there is pooling layers that reduce the size of the feature map. All they do is they look at, let's say, a 4x4 subportion of the previous feature map and reduce it to one number. Here again, this is a 4x4 subportion 2, 4, 7, and 8, and it will reduce it to one number 8. So here what I'm showing is a max pooling. What it does is it looks at these 4 numbers and takes the max of that and puts it here. So it basically takes this whole feature map and reduces its size so that it's easier to process in the next layer. You can also take average of these 4 instead of taking max. The original formulation by LeCun used average. And of convolution pooling, then these feature maps become so small that it doesn't make sense to convolve on them again. So at that time, you would start doing fully connected layers. These fully connected layers are nothing but the formulation of neural networks that you saw. They're exactly like that. Okay. So this was the basic neural network CNN architecture. Now I will go over some of the improvements in basic CNN architecture and training. Okay. So the first improvement that came, which is used very heavily today, that instead of average pooling, people started using max pooling. And the idea is the basics are the following. So let's say this is the result of a previous convolution, and you look at some 2x2 spheres. In average pooling, you would take an average of these 4 and you would get a number 13 here. In max pooling, you would take the max of that and you will get the number 20 here. So in general, both pooling will give you translation invariance. What that means is, let's say these numbers represent whether you detected an eye or not, eye of the cat or not. Okay. So the location where you detected the eye would give you a very high response if your convolutional kernel was in the shape of an eye. Okay. So you would get high response. So let's say here you are detecting an eye and so forth. So what average pooling does, it basically diffuses it over all of them. So it takes an average. On the other hand, the max says that the max pooling basically errs towards detecting a very strong presence of a feature. So why this works is we think that there is a certain distance from detect eye in its close vicinity. So what is important is whether I have really detected an eye or not, or that it doesn't matter whether it is in this where in this neighborhood it is. I will just say that I have detected it, and I will put it in the reduced feature map. The next innovation that came that is now used very heavily in convolutional neural networks is the change in the activation function. So remember when we were talking about these neurons, what they did was they took these inputs, multiplied with weights, added them up, added a bias term, a constant term, and then passed it through some signal that in the previous slide was f. Here it is phi. So if you look at this signal, theoretically what this is doing is it is introducing non-linearity in the system. This non-linearity is important to model complex functions. The classification is a complex function. Complex means complicated. So theoretically, any continuous and let's say mostly differentiable function, a nonlinear function will be fine. So most of the times people use sigmoid. What sigmoid does is for very low inputs, very negative input, it gives you 0 output. For very high positive inputs, it will give you 1 output. So it basically sort of is like a probability of detection between 0 and 1. Okay. And the reason it was used was because it was a smoother version of a step function. A step function would come all the way to 0 here and then jump suddenly to 1 and then stay at 1. So we need differentiable function because when we tune the weights, we want to know whether we want to go slide to the left or slide to the right. If it is flat, if it is not differentiable, if the derivative is 0, then we wouldn't know where to slide. And this tanh function was very similar to that, except that it went from -1 to 1. Now, recently, the standard has become to use rectified linear units, ReLU. So these rectified linear units, when their input is negative, they give you 0 value, and when the input is positive, it gives you exactly the same as the input. So the reason this works better is because it doesn't have an upper limit. Both tanh and sigmoid have an upper limit. So it kind of works like as if it tells you whether it has detected a particular feature or not, and if it has not detected, then it doesn't matter. It ignores the location on which that convolution kernel was applied. So it ignores it in the negative side, and then it preserves its strength going to the positive side. So this has started become the standard now, and it gives a little improvement over the same architecture that uses sigmoid or tanh. Then another improvement that has come is in the training routine. And the way this training routine works is, let's say you are looking at a standard neural network. So these are your inputs, and you have a hidden layer, and they are fully connected, and another hidden layer, and then out. So while training, you would randomly drop out a certain percent of the nodes. So what happens in that case is, let's say you're looking at this output, okay, and this output in this case, when there was no dropout, was depending on 5 different hidden nodes in the previous layer. So if one of them makes a mistake, the other one can compensate for it. Here, if I drop one of these randomly out, then each of these weights that are coming in from the previous layer have to be independently useful to this output. Okay. So if they have to be independently useful, then it helps them learn faster. They cannot rely on each other to correct each other's mistakes. Their outputs become more decorrelated. That means they use the information better. They train faster, and usually the classification accuracy is also slightly better. But once you have done training, then after that you don't drop anything out when you are actually deploying it for testing. At testing time, all of these weights will be there. It's just that at input time, of these at training time, many of these will be dropped out as if they don't even exist. So when also don't exist, both its input connect. In a way, if you think of it's basically you are training many networks. So what these networks random dropout, you would have a dropout, and then in the next training neurons that have dropped out. So it's in some sense that you're training. So whenever you people number of classifiers, and they get better results, and ensemble of the amounts to training an ensemble of new. So in some sense, the features don't rely on each other. They don't compensate for each other's mistakes. Whenever you have add noise to an input, make the training robust, and then it is training many different architectures instead of one, and averages. Miscellaneous of there's a part in how to train the neural network. One is the most important probably is the loss function. Loss function is if you look at its output. This output, if it is wrong, then we have to compute and signal that will propagate back to the weights here. What is there trying to is it trying to reduce the off between the and the actual output? So square would mean that both positive and negative errors would be penalized, or is it trying to reduce like there are loss functions? Basically, in classification, people have error things like cross entropy and some other ones like hinge loss and forth work. So the standard one that is for people fancy loss functions. There have been now libraries available where you compute, you give it a loss function and it computes its derivatives gradient or how to change the weights that the loss minimize. It computes it on its own. You don't have to actually do the differentiation yourself. The other thing is weight decay. You also penalize weights that are very large. What happens when very that you want to be different, but you don't want any to be very large because then it is susceptible to magnifying noise. So you also put a weight decay term in the function. And when you train, there's something called momentum that you use. There are different types of momentum, newer, fancier versions of momentum that have come through. So what this momentum does is when you are training a neural network, it is basically taking small steps to change each weight so that the error or the loss function is minimized. Now, if you take too small of a step, then you would take many iterations to train the neural network. If you take too large of a step, then you would become your training would become it would become reckless. It would miss the region of the weights where it would miss the right step size to actually go back to tune the weights. So momentum adaptively takes larger or smaller steps based on where you are in your optimization function. And then learning rate adaptation. What learning rate adaptation is that you reduce the learning rate when your performance saturates. If your loss function is not going very low, then you reduce your learning rate. The next few innovations that have come in neural networks in CNNs are the structure of the neural network itself. So one is that remember the 3x3 kernel that I showed you earlier? Those actually can be much larger than that. They can be 7x7, they can be 5x5, 9x9. But now people are preferring to use small, only 3x3 kernels, but more of them. So less number of weights because it's only 3x3, not 5x5 or 7x7. It's not going up by square of the size of the filter, but more of them. So why 3x3? Because that's the smallest kernel size that you can have to detect some shape. 1x1 doesn't detect any shape. It only detects one pixel. So 3x3 looks at the center pixel and its relation with the surrounding pixel. So that's the smallest filter size. Then the same type of thing was used in another type of neural network called GoogleNet, in which they used a bunch of small convolutions like 3x3 and 5x5, but they also use 1x1. In the previous slide I told you that 1x1 doesn't detect any shape. So here they are not using 1x1 to detect any shape, but they are using that to reduce the dimensions that are fed to the 3x3 so that the weights, the number of kernels that are required in 3x3 and 5x5 is further reduced. The other thing that they have started using, now let's say if you look at this architecture, this is the GoogleNet architecture, and the input is on the left and the output is all the way on the right, and look at the number of layers that are in between. So earlier when LeNet first came, it had 5 layers or 6 layers. Here these layers now, these are in the 20s or 30s. So if you have such a large neural network, such a deep neural network, these are very deep neural networks. Now if you look at the last layer, that is very close to the output. So it is very easy to train it. And similarly, it's the first few layers, you know that they will only detect simple features like edge orientation. But what about the middle layers? What do they detect? And how do we train them? Why they can get stuck anywhere. So what people have started experimenting with is that you take the middle layers and you see if you can independently get to the output in the middle layers itself. So that will give it will change the weight so that they're discriminative towards the output. So output means the object classes. And then in testing time you would remove this. You would only have the output at the end. Then the most exciting, one of the most exciting architectural changes that has come up recently is in terms of this residual neural network. So what has been observed is that if you take a neural network, a 20-layer neural network, and you train it for a long time, its error reduces. But if you take a 56-layer neural network, its error is higher than that of the 20-layer. Training error. It's not even overfitting on the training data. So why is it higher? If you have more layers, it should at least be able to do as good as the less number of layers, if not better. So why it cannot reduce this gap? One of the reasons is that it has too many weights and it gets stuck in some place where it doesn't reduce the error. And one remedy around that was that instead of taking an input, sending it through some weights and getting the output, a few layers down, you not only get this output, but you add the input itself to that output. Why is this important? What it does is it basically tries to, so let's say you have a shallower network up here and you add a new layer. If nothing else, it will put these weights, it will set these weights to 0 and it will be able to pass the signal as it is forward. So it will at least be able to do an identity mapping. So it should not add any error if you add more layers. So this gap should be reduced. The other thing is that in optimization we know that what this does is it actually models a residual between x and f of x. So when you have such a problem where instead of trying to guess what f of x is in a blind manner, if you try to look at the addition or the difference, then it becomes easier. It's a well-conditioned problem. So now with this architecture, not only have they gone to like 30 layers, but in the paper that I'm referring to here, they have experimented with hundreds of layers, even up to 1,000 layers. So imagine in LeNet we started with 5 or 6 layers, then VGGNet went to like 18, 19 layers. AlexNet was before that was 7 or 8 layers, and then GoogleNet around 20 to 30 layers, and now there are hundreds of layers. And we know that this is better is because there are standard data sets. There are standard data sets for image classification, like ImageNet, which has 1,000 image categories and millions of images. And there's a standard test set in that where any innovation in CNNs they try to compete on that. And we know that the best results have now come from residual nets, these deep residual nets. And again, they use 3x3 convolutions. They are not using any larger kernels than 3x3 convolutions. All right. So now deep learning has become very easy. It has almost become a commodity now. All you need to do is get an NVIDIA CUDA GPU. Why? Because most of the libraries are deep learning libraries basically implement fast convolutions on CUDA-based GPUs, the NVIDIA CUDA GPU. You don't even need to buy it. You can rent a G2 instance on Amazon Web Services. You can use libraries such as Theano, Keras, which is built on top of Theano, Torch, Caffe, TensorFlow, and so forth. And you can go to GitHub or ModelZoo and you can pick up some models and data, and you can start experimenting with them. So I'll give you an example of how easy it is by showing you a Keras code snippet. So here's a code for classifying digits. Now look at this. All it does is it tells you how many images to pick for each iteration, how many classes they're in it, what is the size of the images, what size of pooling you would do, what is the convolution kernel size, load the data, and then you just add a convolutional layer, an activation of ReLU, another convolution activation, pooling, dropout, Dropout was randomly dropping out neurons to train it. Then flatten it means now you will have fully connected or dense layers and so forth. So all these few lines specify your architecture, you compile your architecture, and then you do model.fit, give it training and training data inputs and outputs, and it will train and optimize your network. And then you can evaluate what is the score. In just a few lines of code, you can train a digit classifier using Keras. So, and the other ones are also pretty easy, Torch and TensorFlow and so forth. So it has become that easy now. So the key takeaways are that CNNs are not just a fad. In fact, they give their performance is comprehensively better than other techniques on data that comes on a grid or in some order, images, text, audio. But they need a large amount of training data. You cannot train it on, let's say, a few hundred images or tens of images like support vector machines could have been earlier. You need lots of data, but when you have lots of data, there's nothing better than CNN for certain types of data. They should not be used for data that doesn't allow convolution. For that, you have other deep learning models. Getting started with CNNs is very easy, and code for even latest innovations like deep residual nets is available on the net. So go forth and convolve. Questions? Let me see the questions that I can understand. Can you explain dropout neural network again in brief? So dropout is not a neural network. You have a neural network, and in that neural network you decide that for certain layers I will drop out a percent of neurons while training, and I will randomly drop them out. And when I randomly drop them out, I force other neurons in the same layer to train independently of them. So it's just a regular architecture of neural network, but you specify in your training algorithm that some of them will be dropped out. Is coherent network and CNN similar to each other, or are they different? They're very different. Coherent network is a self-organizing network. It is more used for unsupervised learning. CNN is very supervised. Supervised means that you know what are the output, what output you want. In coherent network, you don't know what the output you want. You just want to find whether the data is organized in a certain way or not. Which is the best tool to start with deep learning? In my view, it is Keras. There are other people who use other tools. Some like Torch, some like Caffe. I think they're all fantastic. If you want to do highly customized, new, innovative CNNs, you want to build your own architecture, then I think Theano is the best way to do it. And your basics will become very strong. But Theano has a steep learning curve. What are other deep learning techniques? Non-convolving. So there are things like long short-term memory, LSTMs. These are used for sequential data. Then there are things like deep Boltzmann machine that can be used for, again, that can be used for like, not like image data, but other things like that I talked about. What are few applications of CNN in text and audio? You can use CNNs for natural language processing, for audio, you can use it for speech recognition. For example, you would take an audio and you would convert it, you would get its spectrogram or Bell frequency coefficients, and then you would use that in a CNN. Can you repeat why CNNs aren't good for breast cancer? So breast cancer, you have to think about what data you are using, right? So if my data is that I have a patient profile, I'm not talking about patient's biopsy image. Okay, I'm talking about patient's profile. So what is her age? What is her birth history, breastfeeding history, smoking history, and so forth. So whether I change the position of smoking history and age doesn't matter. But in pixels, I cannot change the location of 2 pixels. Their order is important. So when the order is not important, then CNNs are not good. What's the future of CNNs? Future of CNNs is very bright. I think we will see more and more applications of it, and not just in like face recognition and images, but also things like reading cancer images and so forth. In a residual network, what exactly is a residual? Residual is something like you have a function and you're trying to estimate it using, you have a signal, let's say x, and you're trying to estimate it with another function h of x, and the difference between them is the residual. So that is what is the residual. How well CNNs can be used for natural language processing? So CNNs have been used for natural language processing. However, there are, in natural language thing, it's not just the, like in images, you are looking at only the pixels to the left and the right and top and the bottom. In language, you have long range dependencies. I can talk about a person in the first sentence, and several sentences later I can refer to her as she, and it should link to the name of that person. So for those long range dependencies, you need memory. So there, these long short-term memories, LSTMs, are better. Which is better, TensorFlow or Caffe? I think it's a matter of preference. Can we use CNNs for OCR of other languages? Of course. We can use, you need a large corpus of annotated images of standard size, and then you can train a CNN for that. ReLU doesn't appear differentiable around 0. Yes, it is not differentiable around 0, but usually our solvers are very good at handling this small quirk. You never get an exact 0, so it will always have a derivative of either 1 or 0. So it is in that way it's okay. Can you explain deep residual nets again? Error again. So residual error, like I just explained, it's x and some h of x. Their difference is that f of x. So because you have that reference signal x, even if it doesn't get it, it will pass x to the next layer. So it doesn't do as worse than a shallow network. Is neural network in a neural network, is the multiply by weight and then addition of a constant the only way? That's the way it has been used till now. There are other ways. There are things like Gaussian units where you take difference of two vectors and then their norm, and then you pass it to a Gaussian function. That's another way of doing it. And that's how, let's say, the Gaussian kernel of an support vector machine also does it. So there are other ways. This is not the only way, but this is the most popular way. Adding weight, multiplying weights with inputs and then adding a constant. Can we use CNN for DVC architecture? I don't know what DVC architecture is. In business context, where neural networks come into play, especially in CPG or banking industry. I don't have much insight in this. I think in banking industry, what I know is that in US, for example, when I use Citibank, I just input my checks into the ATM machine, and it reads it and it credits it to my account. So it does all OCR. So there it is being used. So a lot of, in CPG also, for example, I think it will be used in looking at things like, I guess, matching things in a catalog with other things. So you can use it for different kinds of image recognition purpose. Can you explain why having more layers reduces efficiency actually? So having more layers, you basically increase the number of weights, and somewhere in the middle you lose that error input. Remember, the error gets diluted when you go away from the output. So in the middle somewhere, the error is so diluted that it cannot train those layers. So that is probably the reason why they don't reduce error as efficiently unless you use a residual. Sir, if you create matrix in MATLAB, so how we can see the image of that matrix? That's, please, you can look at it in MATLAB. There's image SC or some command like that. Can you explain a bit of residual? I think I explained that. Can you explain use of layers in convolutional network? Explain that. For predicting odd frames when inputs are two even frames, yes, you can use it for that. I guess you would use some sort of a local batch-based processing. What is the difference between VGGNet and GoogleNet? VGGNet was basically it did not have multiple sized filters in the same layer, whereas GoogleNet had 5 by 5 as well as 3 by 3 as well as 1 by 1 in the same layer. The other difference was GoogleNet in the middle layers, it used a companion loss function to train the middle layers, not just the error that is being back propagated from the final output. Can you explain stride during pooling? So stride is that, let's say you're looking at an image of size 6 by 6 and you look at, you want to pool a 3 by 3 part of it. So the leftmost 3 by 3 you would pool, and then if your stride is 3, then you would skip those the first 3 that you have pooled and you will go to the right 3 by 3. If your stride is not 3, then you can have overlapping pooling. So if your stride is 2, for example, then you would have 1 pixel overlap between one pool field and the next pool field. Is it good to go into mathematical details of CNN or just use the library good for a beginner? Depends on your on what you want to do. If you want to get optimal performance, you need to understand why your neural network is not working. Then you need to understand the mathematics. But if you want to build a quick application, there are standard neural networks that you can use. How can I apply ANN and deep learning into image processing to dealing with images that give me lots of data? Just like I said, you use CNN. Where to apply identity layer? This identity layer is only in the deep residual nets. What are Torch and Keras specifically for? They are for deep learning and CNNs. What data size are neural networks? For what data sites are they beneficial? Usually like hundreds of thousands of images, or at least tens of thousands. How do random forest decision trees compare with respect to CNNs? For image data, they are not better than CNNs, especially if you have lots of data. If you have fewer data, if you don't have lots of images, then probably random forests and decision trees can match CNN performance or even do better. And random forests will do better on that breast cancer type data or the customer loyalty type data than CNNs. What we see more and will we see more and more of deeper architectures? Yes. Other architectures, of course. What are good resources to learn deep learning? I refer my students to Lisa Lab tutorial, but that is based on Theano. Why we need Dropout? We don't really need it, but it actually improves the training. What are the usage of CNN in gaming? I don't know. What kind of hardware would be suitable for build neural networks like GoogleNet, ResNet? Ideally, you would need a large RAM. You would need, let's say, at least like 32 gigabytes of RAM, and you would require a GPU. Don't get a 64-bit GPU, it's a waste of money. You can do everything on a 32-bit GPU and you can get more cores of that. So you want like a 3,000, 4,000 core GPU. Residual explained, what is the optimal amount of data? There is no optimal, it's more is better, but it just takes more time. This might, how can convolution be applied in audio? I have no layers there. No, you have layers. So there the convolution will be one-dimensional along the time of the audio. Can you use CNN for Malayalam OCR? Of course. Why GPU card is required? GPU has a lot of thousands of cores. They are not as capable as your CPU cores, but because there are thousands of them and you are doing the same operation convolution at multiple locations in the image, that's why it becomes faster. It does thousands of those operations quick in parallel. Is expertise in Python a must for learning deep learning? Yes. Most libraries are in Python. CNN, now the MATLAB 2016 has CNNs also. Unfortunately, we have run out of time. It was a pleasure to give this seminar, and I hope you got something out of this seminar.